Good morning, everyone, and welcome to the Society of Maritime Industries and the Marine Autonomy Challenge webinar. My name is Tim Curris. I'm the Programme Director here at the Society of Maritime Industries, but also Secretary to the Maritime Autonomous Systems Group Council. My job today is to facilitate this webinar. As you will be aware, we are holding it in place of the on-water finals of the Marine Autonomy Challenge, which we unfortunately had to postpone this year. But we have an interesting lineup, including the University Centre of South Devon team, who will describe to us how they were planning to approach the challenge. Danielle Berenbaum from L3 Harris, who will give a recent graduate's perspective on joining the maritime industry. The University of Bath team, who have been working on a final year project based on the Marine Autonomy Challenge. And Hugh McLean from Autonaut, who will talk about the challenges in the design and building of an autonomous surface vessel. We will then have a panel session for any of your questions. First of all, however, I'd like to hand over to Geraint West, who is Chair of the Maritime Autonomous Systems Group Council, to tell us a little more about the Marine Autonomy Challenge. Geraint.
Good morning, everybody. I'm sure, like many of you like me are getting a bit of webinar fatigue. So I really appreciate you taking the time out to join this morning's webinar. As Tim referred to, we've had to hold this instead of doing the on-water competition, and I'm still incredibly disappointed by that, having to cancel that. But I thought that hopefully today's webinar underlines just how important the MA Challenge continues to be, and it continues to be one of Council's highest priorities. And that's because a key part of Council's mission is to encourage young technologists and help them develop careers that contribute to the future of the UK's mass industry. That will continue to be the case. So I just wanted to reiterate a little bit about where MA Challenge came from and why we launched it. The aim of the challenge was focused on autonomy, so not about building platforms, but looking at behaviours. We put a focus around that to think about how autonomy might address the problem of plastics in the ocean. We had another aim to stretch the knowledge of the students and promote creative thinking, a little bit outside their comfort areas, hopefully. As with any of these things, we want to encourage team working through a variety of individual skills. And the last one, which is one of the reasons why this morning's webinar continues to be an important plank of this, is to connect the brightest young talent in our universities with key players in the industry. So to do that, we were going to provide powered surface catamarans, which would include a battery and thrusters provided to each team, leaving the teams to design, install control and sensor systems, and then demonstrate controlled, safe manoeuvrability of vessels under challenging conditions. You may recall that the competition had two phases. One of those was a video submission, and we had 9 submissions, with the 5 finalists that were selected in alphabetical order being University of Birmingham, University of Cambridge, University Centre South Devon, University of Newcastle and University of West of England. Now, unfortunately, not all of those could join us this morning. I mean, as I think everybody realises, COVID-19 has created some amount of turmoil in university calendars at the moment, and we certainly understood that many people found it impossible to join us this morning. But we wanted to keep this thing going because we really do see this as a high priority. So without further ado, I'm going to hand over to the first speaker. Thank you.
Thanks, Geraint. That sets us up nicely. So it's over to you, Matt, from the University Centre South Devon, to introduce your team.
Hello. Yeah, thank you for the opportunity to speak. My name is Matt Prowse. I'm a lecturer here at the University Centre South Devon. So we embarked on this project. We were actually doing something similar. So we do a design project every year with our level 4 and level 5 students. So we were looking at a similar project. We were looking and evaluating, I believe it's the Waste Shark, which follows a sort of similar theme. And then it was just by chance that we came across the Marine Autonomy Challenge, and we decided that, it would be a good project for the students to engage with industry as well. So our location, because we're based around the Torbay area of England, we do see the waste problem quite predominantly around harbours and marinas. So that was why we were currently looking at this project. But yeah, it was fantastic. It was really, really good. You know, the engagement we had with the students was fantastic. I think they ultimately were the drivers of this, probably, you know, because they feel very passionately about it as well. So that was really good to see. And in terms of projects, I think this was probably the first project that we'd actually collaborated with numerous other departments rather than just us as a marine department. We were actually seeing collaboration between our computing, between our digital media, even our automotive and sort of bodywork department were quite keen and interested. So we were actually working on a sort of whole design of our own before we came across the competition. So, you know, even if we weren't accepted, which we were, you know, we were going to carry this on in the background. But I think, you know, again, talking about student engagement, they were the real drivers of this. And, you know, even after COVID, you know, to embrace the online sort of operations in the way they did. And I said this in another meeting the other day, that, you know, we currently operate on Microsoft Teams, and I could see the students working on this project up into the late hours of the evening, you know, and sometimes getting questions after hours when, you know, well, what do we do about this? What do we do about this? So, you know, that was really fantastic to see. And I must say a thank you. I think Joseph Ross is here. So he's another lecturer at the University Centre South Devon. He's in our sort of programming and computing department. He was an inspiration to work with as well. So again, to bring in all these different elements, because you know, it's not just about marine, it's also about, you know, bringing these sort of different skills together. So unfortunately, the students have finished now, so they couldn't be here with us today, but I know that if they could have done, unfortunately, they were all working. So again, that's probably a good thing considering the situation. So what I'm going to try and do now is try and play the video. So this was, put that full screen and share.
Hello, so my name's Joe. I'm the team lead of 5 students. We are currently studying an FDSC in Marine Technologies and an FDSC in Manufacturing and Mechatronics.
My name's Kit. And my name's Ollie, and we're a part of the design team.
My name's Andrew. And my name's Len, and we're the program team.
Welcome to Team Project 15. We are from the University Centre South Devon, based in Paignton. My name is Matthew Prowse. I am the project lead and lecturer on the FDSC Marine Technologies. Also to acknowledge Joseph Ross, who also works at the college and has supported this project throughout this year. So yeah, I'm going to introduce you to the students. They are Joseph Oram, Kit Monaghan, Oliver Hare, plus Andrew Hurst. They've been working really hard this year on Project 15 and the Marine Autonomy Challenge, and hopefully they're going to demonstrate that in this presentation. So leading nicely on, I'll pass you over to Joseph Oram, who's going to talk to you guys about the background and introduction.
Hello. So yeah, so today we're just going to briefly talk about these things on the slide here. So we're going to discuss the design of a marine autonomous surface ship, also known as MASS, which will hopefully identify and remove plastic from the ocean. So we're going to begin with identifying the background, the problem that is plastic in the ocean. And then we will move on to the design process and solutions that we have come across certain problems during that process. And then we will talk about programming and solutions again to programming problems that we have come across. Next, though, I'm going to discuss about the background content. The waste impact upon the environment is absolutely devastating. especially plastic waste in the ocean. In 2010, 192 coastal countries generated 275 million tonnes of plastic waste. This plastic is ingested by all sorts of marine life. Veterinary records themselves stated that over 100 species of birds, of marine birds, are an example of the plastics and waste being ingested by marine life. The financial cost is also high. The government released the figure for keeping the UK streets clean in 2016-17 at almost £30 per household. We believe that mass can be a solution for reducing financial costs and environmental impacts. Next, I'm going to hand you over to Kit to talk about the design brief and specifications.
Hello, my name's Kit, and today I'm going to be talking about the design brief and specification for our team's project and our vessel. And we've had to consider the three challenges that the MAC Challenge have given to us, which are navigation, colour identification and speed. So the vessel design will have to be programmed to navigate through an obstacle course composed of different coloured objects and be capable of operating at high speeds to be able to surpass rival groups' vessels without collision. We will need to take into consideration the weight of the vessel to obtain a suitable speed and stability to help navigate the course efficiently. In addition to this, environmental aspects such as the wind and tide will need to be overcome to complete the challenge, whilst also considering certain suitable corrosion-resistant materials inside our vessel. Other than this, the regulations we've had to comply with are the Maritime UK Industry Code of Practice, which we have taken from that we would need an all-round white light for visibility whilst we're at sea, and all of this is going to have to come within a £500 budget, provided we're given the hull already by the MAC Challenge team. I'll now hand you over to Andy to talk about the programming.
For the computing, we had a choice between a Raspberry Pi and an Arduino. The Raspberry Pi is what we chose because it has built-in Wi-Fi, which means it can communicate better with other devices. As well as this, it works better with Python, and the Arduino uses C. And our team, as a whole, has more experience with Python than Arduino. A Raspberry Pi can also do multiple threading at once. This means it can do multiple processes, so it can quicker and do more calculations at once, meaning it's better suited for data calculation. For data transfer, we had to choose between a 4G dongle, a mobile phone, or radio transmitter. We chose the 4G dongle because the mobile phone would take up too much of our data, and the radio transmitter would not be able to communicate with other devices as well. For example, our website and anything else we use to communicate with the drone. And for location, we had to choose a GPS chip with a gyro compass and a mobile phone. The GPS chip with gyro compass would have everything we needed, be able to tell direction and where it is, and would not take as much as a budget as the mobile phone would. For movement, we created two flowcharts. The flowchart on the right defines the forward movement, where 0 being off, 1 being on, and 2 being backwards. So if you wanted the drone to move forward and to the left, you'd have the right motor on, left motor off. And the other way around for going right. And to go in reverse, both of them will be in reverse. This is very simplified, as we would have a multi-speed system rather than just 2-speed. For the rotation, it's done by the left algorithm, which works by powering the motors individually. So when the left motor is in reverse and the right motor is forward, then the drone will rotate on the spot. This would all be calculated by the Raspberry Pi within the drone. Collision avoidance would be achieved using a series of ultrasonic sensors placed around the exterior of the hull, meaning that if there's any obstacles in the way of the drone, then it would detect the objects and move out of the way of it. This works by having the ultrasonic sensor send out a signal which, when it hits an object, will bounce back and be picked up by the receiver. It would use the speed of sound and how long it took to reach the object to find the distance away from the object. Colour detection would be done by the Raspberry Pi. It would have a camera mounted on the phone which takes a snapshot. This photo will be analysed by a Python program which will find the colour at the centre of the frame and use an algorithm to detect the colour and select it from a database. This would work well with contrasting colours, and it would have a select few colours in the algorithm which would be able to detect from. So this is so that if there is any colours which are similar to anything else around, it would be a better detection because it would already detect for those colours. I'll pass you back to Joe for navigation.
Yeah, so for navigation, we will have to plan our route before. We will begin by typing in the required GPS coordinates and to create checkpoints for the direction of travel into the user interface. So then the initial route is then planned. The current location is then compared with the destination, and this is something that will happen throughout the whole voyage that the vessel will be taken on. The distance to the next checkpoint can be calculated using the current location, Pythagoras' theorem. The required bearing is then calculated and the new heading is obtained. The vessel will alter course if required, while constantly analysing the bearing and distance to the checkpoint. The code will cease when the vessel is within a radius of the checkpoint. Visual sensors will be used to locate the buoy. So that is our essential basic navigation. We would use the code on the right hand side of the screen, and then this is all used together. And now I'm going to hand you back to Matthew Prowse, who is going to talk about our future projects and our current project 15.
Yeah, so thank you, Joe. So yeah, I just wanted to demonstrate a bit about what the students have been doing this year. So regardless of the Marine Autonomy Challenge, we were already working on, and we called it Project 15 because the students came up with it and they thought it was a good, and it is, I don't know why I'm saying it, but anyway. So yeah, so as I say, the students have basically designed primarily like a catamaran, which ultimately is going to drive through the water and pick up litter as it goes along. So as you can see from the diagram, the way it's shaped is ultimately it basically scoops up litter as it goes through the water. So we used a program called MaxSurf, which we use for our sort of whole design. Then from that we can basically create shape using we've got an industrial laser cutter which we basically then used to make a former, which then we were going to make a plug to basically make the hole. So this is already in production at the moment. So this is pretty much the stage we got to before we went into lockdown. So again, next year all the students that you've just heard from will be coming into the second year. Ultimately, it's hoped that we can progress the Marine Autonomy Challenge, or if not, we will be progressing Project 15 as it is. So, you know, we're really passionate as a group and as a team that, you know, automation is the future of, you know, cleaning up the oceans. Okay. Again, one of the reasons why we're very passionate about this is that we are in what we call a local seaside town. And you know, you only have to walk around the local area to see that this is a problem and a global problem as well. So hopefully when we get back in September, we intend to do some testing to get the vessel on the water and start, you know, building the algorithms and the programs. So thank you very much for listening. thank you to the students as well, and hopefully we'll see you all next year.
Matt, that was great, thank you. But we'd now like to introduce Danielle Barenbaum from L3 Harris, who's just going to provide a perspective of her experience as a recent graduate of joining the industry, and just going to give us an overview, which we thought would be interesting for our budding marine autonomy engineers. Danielle.
Hi Tim, thank you. I will just try and share my screen, put some slides together. Yeah, okay, great. So thank you everyone for listening to my presentation. I'm going to give a short overview of my journey and my experiences as a graduate through to where I am now. So for those who don't know, L3 Harris is a global company providing services throughout the world's air forces, navies, armies, as well as the commercial sector. I work at L3 Maps Limited, which is a subsidiary of L3 Harris, and we specialise in providing a world-leading safety critical solution for over 22 navies. Our integrated platform management system delivers tailored solutions for ship navigation, communication, automation, ship support, spares, and even training. So I started off, I went to the University of the West of England, which is quite fitting. I studied aerospace engineering, which was a 3-year course. During the 3 years, I did various different modules such as fluid dynamics, maths, and project management. But towards the end of it, I still wasn't very sure where I wanted my career to go. I didn't know what sort of direction I wanted to go in, whether I wanted to be specialised or not. So I knew that I wanted to find a graduate scheme which could sort of ease my transition into the working world and hopefully round myself as an engineer even further to sort of see where I best fit. So I had a look for graduate schemes and found one at L3 Maps in Bristol. I was part of the first year of graduates that they took on as part of the Giants scheme, which is the graduates, interns and apprentices nurturing training scheme, bit of a mouthful. At the moment they've got 5 apprentices, 3 graduates, and that have completed the schemes. There are 4 apprentices and 3 graduates which are now in full-time employment with L3 Maps. It was a 2-year graduate placement in which I did 4 6-month placements, which for me I felt was better than doing 1 long placement because it meant that I got to try out different things and see where my skills were best placed, what I enjoyed the most, what challenged me. So that was perfect for what I really wanted. I did software, hardware, systems engineering, and then 6 months in bids and proposals. I covered a great range of tasks. I learned lots of new skills, but I suppose the downside of it being for 6-month placements, especially in the marine industry, a lot of projects can be very long. They can be months, years, sometimes decades of work. So a lot of the time, some of the work that I was doing was quite light touch because there was only so much that they could give me. But it still meant that I was able to take on that knowledge and find where I best fit. During my placement, I went to various different trade shows. I was lucky to go on the Prince of Wales while that was being built, still is, I suppose. And it was a really good way of sort of seeing what other companies were doing as well. I got to interact with other sort of new young graduates in the industry. A few pictures of what some of our apprentices and graduates have done over the years. It's a really good scheme in my opinion, and I think it was perfect for what I wanted to get out of the scheme. So once I finished my scheme, I got a role as a system design engineer, which was for me the perfect combination of the engineering, research and development side of things with the customer facing, faster paced work, which I had experienced within the bids and proposals team. I still carried on with various different events, like in that picture there is the Young Engineers events on HMS Sultan, which were really good. And I've further sort of honed my skills in technical proposal writing. I've written a technical paper which I presented at the International Naval Engineering Conference in Glasgow in 2018, which was terrifying, but a really useful experience and really grateful that I got to do that. And also working on designing solutions as part of the engineering side of things. I did various different research and development projects individually. What you see on the right here is a tank and pump system, which we built in real life as well, which was to give me and others experience in the control and automation side of our work and see it put into practice, which obviously when you work on military vessels is sometimes quite difficult to actually see your work put into practice. It was lovingly named the water torture project at my work because it presented various challenges. As an R&D project, obviously there's always something which is high priority, there's always something else which needs doing before work on that needs doing. But it was the perfect opportunity to de-risk this potential new solution with a new IO, with Vargo IO systems for projects which we then have used for Type 31 for IPMS. So going over to Type 31, I am the systems engineer currently for our Type 31 project in which we're providing the IPMS for. I was lucky enough to write the technical paper as part of the bids and proposals team, and then of course we won the contract, which was brilliant. Throughout my time I've owned various different packages of work. I've also worked with other L3 sites in the UK, Canada and India to get various pieces of work done. And quite recently we got the project through to a successful preliminary design review where our progress was assessed against the schedule and requirement compliance. The picture on the left there is just sort of a high-level overview of what the IPMS system can look like. So what's next for me? What's next for L3 Maps? Obviously, as a company, we've worked on QEC, Type 26, and now Type 31, providing IPMS and other extra capabilities. We'll be pushing Type 31 forward for the critical design review in a few months, which I'll continue with my much heavier engineering role, which I really enjoyed. I'm also doing a part-time master's degree with the Marine Technology Education Consortium. So that'll be an MSc in Marine Engineering. Personally, I wish I'd done it while I was still at university. It's a lot easier to do it then. Now I've got a full-time job and a part-time degree, which is hard work, but I'm very lucky to have a very supportive company which has allowed me to do it. So that has been really brilliant. So that concludes my presentation. Might have been a bit quick. I'd like to thank you all for listening again. Hopefully I've given you a little bit of an insight into my journey and my experiences as a graduate and then through into the working world, and whether what you've heard you've loved or you've hated. Hopefully it's given you something to think about, and I look forward to any questions later on. Thank you.
That was great. Thank you very much, Danielle. Some really great inspiration there, I hope, for those budding marine engineers out there. There's already a few questions stacking up in the chat, which is great. Please submit any you have for Danielle, and we'll take those in the panel session. But now I'd like to introduce Rahul Jury from the University of Bath. The Roll's team have been working on a final year project, I think, which took its inspiration from the Marine Autonomy Challenge, and he's going to tell us now about their team's progress. Over to you, Roll.
Thank you, Tim. Can everyone hear me? Okay, great. Yeah, so I'm a student from the University of Bath. My course mate Katie was meant to join, but I think she had something on, so she had to change something last minute. So we were one of the teams that applied for the MAC challenge. We initially went through the spec, and we were going to do it in parallel with our group business and design project, where basically we design a product and we come up with a business plan around it. In the end, we didn't get through to the MAC challenge, but we did take we took the specification for it as a guideline, and this general problem as a guideline. So I'll start sharing my screen to show what we've been doing. We have a little poster that we've made. Can everyone see? Okay, so yeah, we're a team of 6. I was the technical lead on this project. Katie who was going to join us, was the design lead. So she designed the catamaran, the physical features, the CAD around it. We had 4 others as well. We had Elida, Buket, Cecilia, and Peter, who were business lead, project management, R&D, all of that. So when we started with this project, we looked at it kind of heuristically. So we did a bit of research into how plastic waste accumulates in the ocean. So we're looking at existing companies like the Ocean Cleanup. We looked at existing solutions like Waste Shark, what they were doing, and kind of comparing how we can do better. So we found that one of the big hotspots for plastic collection, plastic accumulation, was in East Asian countries like Indonesia and China. This is where millions of tons accumulate every year, far more than in the States, where there's only about 100, where it's about 1% of that amount accumulating at the coastline. And we also found that it was, the biggest problem was that when plastics would drift out into the coast, they would eventually degrade into microplastics, which are much harder to collect as they sink to the ocean floor. And these degrade into smaller plastics from UV rays from the sun. So we kind of came up with this specification. We want to target macroplastics, plastics pieces greater than 5 millimeters, like bottles that have just gone out recently. They mostly accumulate on the coastline. Also, because we're targeting regions in East Asia, we kind of want to go low cost so we can incentivize them to purchase our technology. And we wanted to go, of course, for a sustainable design, because when you're making something like this in such a hazardous environment, it could easily be trashed and you could end up doing more harm than good. So that's something we were mindful of. So our mission was to detect and collect plastics from the ocean surface using an autonomous surface vehicle. We used as a baseline the vessel from the specification. It was a 2-meter catamaran with twin thrusters, twin bluefin T200 thrusters, and we built on top of that. So this was our design process we went through. We did a morphological table of little concept of all of our little functions. So there was control, there was collection, detection, navigation. So we made a little morphological chart, and we made a couple of concepts to combine them before we finally came to something looking a bit like this. It deviates a little bit from the specification that was given from the MAC challenge, but it's pretty similar. And in the final design, it's powered by a big lithium-ion battery pack with solar panels as a backup in case it gets stranded. We have these collection cages with pontoons for balance. We have a control system with a Raspberry Pi and an Arduino running an AI algorithm. For detection, we have a camera with a neural network algorithm for detecting plastics and obstacles. And we have a bunch of other modules for navigation, which I'll tell you about soon. So the way we broke up this problem was we decided, okay, there's 4 major subsystems in this system. So there's collection, there's control, there's detection, and there's power. Yeah, so those are the 4 major ones we decided. So each of these 4 was assigned to one of us. And then for the last 2 of us, one of us was in charge of integration of subsystems and project management. And the last of us did these 5 smaller subsystems that didn't require as much work. So yeah, for collection, we wanted to go for a passive method. We iterated through a number of ideas, but we went through a passive method. So lightweight aluminium cages that passively collect plastic. For the control system, we have a Raspberry Pi and an Arduino. So the Raspberry Pi runs the neural network algorithm for detecting plastics, as well as a mission planner, which can alter the course of the vessel as it detects plastics. And the Arduino acts as a slave to the Raspberry Pi, so it can interface with some of the modules we have, which communicate via I2C or something. So for detection, we decided to use a combination of a Raspberry Pi camera with the neural network algorithm and a laser rangefinder for detecting for getting a point cloud of distances away from the vessel. And for the power system, a lithium-ion battery pack, along with a set of solar panels in case the vessel gets stranded. And then for the smaller subsystems, we had cooling, communication, navigation, propulsion, and environmental resistance. So cooling, we just had a fan and a heat sink on the ESC controllers for the thrusters. So for communication, we used a module that communicates with the Iridium satellite constellation. Because one of the things in our specification was that this has to go up to 8 miles out from the coast, because because 8 miles out is the territorial limit for that country's ocean, and the plastics can drift quite far out as well. So something like radio or cellular wouldn't have been reliable, so we needed satellite communication. For navigation, we wanted to develop our own GNSS-INS fusion module, but it would have taken too much time, so we've chosen an off-the-shelf module for GPS, for combining GPS, and also a magnetometer and an accelerometer for dead reckoning. For propulsion, we went with the thrusters that they provided with the challenge, the twin T200 thrusters, capable of providing up to 500 watts of thrust, or about 72 newtons thrust. And for the environment, we added a radar reflector, a light, and a pinger, just to comply with some maritime regulations. So to sum up how this thing works, someone from a base station will designate an area for one vessel, like a hectare wide. They will, using some satellite imaging, will find, okay, this is an area quite relatively dense with plastic, and will tell the vessel to target this area. And then the autonomous system inside takes over, and it will sweep the area, and it will collect plastics it finds along the way, while avoiding collision with other obstacles. So it's designed to be autonomous within that area that the operator sets. And then once it does, it returns to shore and the plastic can be emptied and collected. So, and we wrap this whole product around a theoretical business plan. So we wanted to be an NGO. We wanted to do something similar to what the ocean cleanup was doing. So they're an NGO who have made like an artificial moving barrier that collects plastic in the Great Pacific Garbage Patch. They've had mixed success with it, but they're one of the more well-known solutions. And I think one of their newer projects, which collects waste in a river, is doing better. But we wanted to go for an NGO kind of route because we're targeting areas in East Asia, China, and Indonesia. So, and these are countries that maybe don't have programs that are very active towards solving this problem. So we want to step in and kind of help. So yeah, that's why we want to be an NGO. And the plan is we'll prototype this. This is all hypothetical because we didn't have any hardware to work with. The plan would be in the first year or two, we would prototype the ASV in Portsmouth, around where Autonaut is, and develop it to a reasonable level. And then we'd start our initial cleanups in China. And then over the next couple of years, we'd try and roll out over Indonesia and the Philippines and other countries that are quite prominently have this problem. So yeah, for financing this project, we do a bit of crowdfunding. We've been a little optimistic with how we fund it, but it's a similar model to how other organizations are trying to tackle this problem. So we think it could work. And finally, so again, because we didn't have access to real hardware, and because a lot of this is very hypothetical, we did some simulations. We did a lot of white paper research, but you can't really say this is good for sure. You can only go so far in how detailed you can get some aspects of the design done without eliminating uncertainty. So we had a lot of future considerations. And a few of them were included. Okay, so we want to account for weather disturbances in our control system, maybe use a wake propulsion system. It would be a lot more efficient, but it might not work in some areas of East Asia where tide is always really low. And also use just generally better detection hardware. And yeah, that sums up our project.
Great. Thank you, Raoul. That was really interesting, and again, I think it's given us some ideas for expanding the challenge for next year. That's great. If you could stop sharing your screen, I'm now going to play a presentation from Hugh McLean of Autonaut, who's just going to give us some overview of his lessons learned in designing unmanned marine autonomous systems. Hugh is online and he'll join us for the whole session shortly. We are running over time, but we're gonna press on, and we're still going to ask some questions. So I'm afraid we will run over a little. So I'm now going to start to share my screen.
Good morning, my name is Hugh McLean, and I'm going to talk to you today about the lessons that I've learned in designing unmanned systems, from the drawing board up to completing offshore deep ocean data gathering missions. As I said, my name is Hugh McLean. I'm a ship science graduate from University of Southampton, and currently I'm working as engineering manager of Autonaut. So I have the responsibility of the design and building of the Autonaut, I've also been a key member of the operations team in operating Autonauts all around the world for different range divisions. So firstly, I'm going to explain what an Autonaut is, for those who don't know. Then going to look at advantages and common errors in testing programs, and the advantages to prototyping, model testing, and full-scale testing. Have a look at the difference between when to use off-the-shelf parts and when custom bespoke parts are better. Also have a quick look at the mechanical and electrical system interfaces, and a brief skim over the sort of full-scale, big picture designing of systems which you need to incorporate electrical, mechanical, and naval architecture. So firstly, Autonaut is an unmanned surface vessel which is wave propelled and solar powered. The wave propulsion works by the waves rocking the hull and moving underwater wings, allowing the boat to swim forward without using any fuel. And the solar panels on top power the electrical systems on board, which include the autopilot system, onboard auxiliary systems like the nav light, the radar reflection, as well as the onboard payload, which can be arranged in sensors capable of collecting different data samples, depending on what the mission capability is. Because it doesn't use any fuel, but none on board, both capable of very long endurance missions, and able to collect a whole range of different data, depending on what sort of sensor payload you mount on the boat. It's easy to launch, so you can launch it from a slipway or from a crane. And from a crane it could be off a dockside or out at sea off a ship. The boat's not fast, only going sort of a couple of knots most of the time, and is able to stay on station if you want to by just circling around a waypoint. But the system has to be very robust to survive any sort of storms or any other sea state that you can see. Advantages and common errors in testing programs. I mean, one of the key things is to understand the goal of the testing and make sure it's nice and clear what that is and how you can achieve that. It's a good idea to try and do some real-time analysis to look at as you go along to assess how the performance is going, to try and identify any interesting areas as you're going. It's quite basic, but any analysis you can do during the testing to understand the performance is very helpful. When designing the matrix of the testing matrix for all the tests you want to perform, it's important to try and look at comparative tests. So these are tests that side by side are pretty much exactly the same. You're only changing a single variable, so you can have a better understanding of how that variable impacts the performance of the testing. It allows you to be more targeted with your testing matrix to try and identify and understand the areas you're looking at to achieve your goal. It's also important to understand the limitations of your testing. This will have big implications of which areas you want to concentrate on, which areas you don't. While you're doing the testing, it's really important to write down notes and to use as many pictures and videos as you can. And this will help for when you come to data analysing, having a better understanding of what definitely went ahead and to confirm and back up your memory of what happened to help for more detailed analysis later on. In testing, eureka moments don't really happen, but you more or less find that's a funny moment where you find something interesting in the data, which you have to go through, confirm that's what happened, and that's where the interesting discoveries come from, away from the data sets. So it's important to have as much opportunity to do that as possible. So the advantages and differences between sort of doing full-scale prototype testing or model testing, getting back to knowing the limitations. Full scale, you get much more direct results of direct components, but it might not be as cost effective, and you might not be able to do it as a controlled environment, which means you can't control enough of the variables to make it accurate testing. Whereas model testing, you can do much more cost effective for a large matrix, and you do it in much more controlled environments, but you need to understand what the limitations of the scaling effects are likely to be, and how that implicates the testing program and how much value you can get out of it. So there's times where off-the-shelf parts will be better, and other times where you'll need to design and build your own custom parts. For off-the-shelf parts, you've got the advantages of economies of scale, as let's say lots of parts for multiple users, and they can sell them for much cheaper, and it's designed, built, and tested by another company, so they will have those overheads. But the issues with off-the-shelf are you don't have control of the quality, and you don't have all the control of the availability. So they might not always be available to the standard that you want, or numbers of might not be available. Functionality of it, they might have different priorities as what functionality is important to them, especially with developing the system. So you don't have as much sway over that side of things. If you need more of that, you need to be more in control. Then design a custom part is better, because you get to design it and build it yourself. So you get full control of the quality, availability, and its functionality. But you'll be producing large numbers of those parts in most cases, so you won't necessarily get the same economies of scale. And then you also need to have a review of what your team's skill set is, about whether you have the capabilities to design that part to the level that you require. So it's a good understanding of what your team's capabilities are. When it comes to your teams, you're likely to have a split between mechanical and electrical systems, and the interfaces between these parts and the interdisciplinary communication is all very important to get a good part going forwards. So it's important to sort of define the interfaces early on, because these will have quite large implications on designing of each part or each of the components. And for the designs that will be successful, you want to allow for a level of evolution from both sides, because this will allow you to get understanding, learning from either testing or missions, so that to improve the quality and move things further forward. Level of modularity can allow for different systems to be changed out and switched up and upgraded, which can be very useful. But you also want to make sure you're not overcomplicating the system by forcing modularity into places, which adds more complication and chances of making the product more complex. So a few ideas there of things to look out for. When it comes to doing full system design, sort of design spiral is the classic view of it. It's important to keep that in mind when you review the process. So you want to start off with the concept, and then start going out of it with operation requirements and how you understand it. It's important within your team to understand who's responsible for each part, and have some level of accountability for each component to make sure stuff is working forwards and being used. And the key is especially when designing complex systems like this, is to make sure you learn from everything you're doing to make it better going forwards, and try and improve the language you communicate in. It's very easy to not understand the different languages between. I'm not necessarily talking about English and French here, I'm more talking about shorthand, talking in engineering about electrical components, interfaces, serial connections, mechanical toys. So it's key to make sure you're communicating evenly and fairly in a team, and that's how we'll get more productive, and have a look at what tools you've got available to do that. Thank you very much for your time, and I'll be available for questions later on in the webinar. Thank you very much.
Tremendous. Thank you very much, Hugh. That was a great presentation. Right, so we're approaching 12, but we've got a whole load of questions which I would like to ask a few. So we've got the panel. Everyone who spoke this morning is available. I'd like to just perhaps ask one each to make sure we can get through without going really over time. So Matt, I'd like to if you could tackle your questions first. Perhaps you could try and attempt to answer those that were aimed at you. First of all, how does your team come across the code of conduct, which I believe you referred to?
Yeah, so we found that, well, it's actually in combination. So I'm currently studying a PhD at the moment in automation and phishing. So I was aware of the code of conduct prior to this, but actually one of the students came to me and said that he'd found it through his own research, through the stages of research that we did prior to the competition. So yeah, there was another question said, how would we develop any sort of testing environments? So we were actually in conversation with our local harbour master. We don't actually have, well, we have access to model testing facilities at Plymouth University, but we've also got quite a luxury of, well, the sea around us where in our location. So we were in talks with Torbay Harbour Master about having a test bed down at the harbour where we could actually go and test for real. So that was quite lucky. And our Marine Academy is on the River Dart as well. So we've got access to sort of tidal river as well, which was quite good. So yeah, and then I think there was another question about, so yeah, I mean, again, we were quite lucky in a sense that because of the access to sort of equipment that we had, we were actually testing a lot of the electronical systems, you know, in mock sort of scenario. We didn't actually have the full prototype working, but we did actually mock up all of the sensors, the motors, to actually test the algorithms to make sure that they could work. So we were very confident. It was such a shame that we didn't actually get to do this for real, because again, the students were so excited about it, which was good. So yeah, I think that's it. There was another one about capacity, making sure about cargo full. Again, I think we were talking about sensors, making sure that, you know, once the cargo, and I think we did actually, because it was ultimately all going to be driven from a website, so we had a capability to override the system to go to sort of manual control if we needed to, if there were any problems. But ultimately, you know, the operator could sit at home on his computer and actually be monitoring the system, and, you know, cameras, sensors, things like that. So again, I think Joe could probably answer some of these questions better than me. But so yeah, but I'll move on because I know time's not a luxury. So
no, well, thank you, Matt. Thank you for trying to tackle all of those questions for you. That was great. So Danielle, I'd like to ask you a question. I think there's one there for you about from Jeff about how have you found networking with others in the maritime industry?
It's definitely one of the things where you have to go out and find it, especially with young engineers in the industry. I've been lucky enough to, there's a few boards that I'm part of, like the MMS Enterprise Skills boards. I've been to a few events that they've run, which they really focus on getting young people within their companies to get to go to these events. So you do get to see the same sort of faces, which is good. And things like DSEI and INEC as well. It's good to go to these various events where you get to see the same people at different conferences and trade shows like that. So I find it okay, and it's nice to get to speak to people that are going through the same sort of things as you, that have been through the same experiences, have often done graduate schemes and stuff like that. So it's nice to share whether we've enjoyed how we've done it, what's been good, what's not. And we went to one recently which was specifically looking at how to improve the sort of transition from a graduate scheme into the working world, and making sure that graduates aren't just sort of forgotten once they're in a full-time job, and they still have that sort of support to develop themselves within their career. So I found it fine. It's been quite good, actually.
Excellent. Thank you, Danielle. I'd just like to ask you one question, actually. What's the most important piece of advice you'd give to those students out there who are looking to join the maritime industry?
Ooh. Personally, for me, it sounds like I'm just sort of tooting the horn of my own company, but if you can find a company, if it's L3 Maps, great, that can give you a graduate scheme which really does support you, like I was in mine, I think it can make a huge difference. A company that's willing to invest time and money to send you on training courses and to different shows, rather than just sort of throwing you in at the deep end, I think that's invaluable. So I think if you can look into other people's experiences, like someone might get from my presentation and from my journey, then I think that's really worthwhile to do.
That was great. So sorry to bounce you on that, but thank you.
No,
Great. Raoul, I think we'll move on to you. There's a couple of questions for you. We like the inclusion of the business plan. What were the key areas of design that the business plan affected?
So to be honest, the design of the product more or less came first. Well, we did the business and product in parallel, but we started first with working from the specification of the Mac challenge. And as we were initially looking at the problem of how can we most effectively collect plastic, just simply that, ignoring using any vehicle, fixing ourselves to this kind of solution, we looked at what existing organizations were doing, how they were, because there are commercial solutions like Waste Shark, they're just selling commercially to, I think they've sold some to Dubai, some to the Netherlands, I think some to the States as well. And there are obviously the non-profits as well. So, yeah, okay, so one main part of the design was we had to use cheap products, or at least, especially for the prototype, we had to use off-the-shelf products, because we wanted to deliver. So we allocated a certain amount of time to prototype this product, and if you wanted to deliver it in time, we were going to go for off-the-shelf parts. But then we also said for a later version, we'd try and design some more bespoke parts, also maybe with a higher cost once we've established ourselves as an organization. I hope that answered the question.
Great, thanks, Raoul. There's a question here from Core IB. It was addressed to Danielle, but I'm not sure. I think it might have been aimed at well, any of you actually. You know, it's around dealing with the issue of high frequency noise in antennas on the sea, as well as how do you deal with emergency situations with autonomous systems at sea? Could I ask that of any of the teams, including Hugh, who've been looking at this, how you've dealt with those issues?
I won't. To be honest with you, we probably didn't get that far into the project, but it's certainly a valid question, definitely.
Yeah.
Yeah, I can answer this from sort of the Autonomy perspective for having a system that has operated. So if I concentrate more on the presence of emergencies, the key here is trying to understand what the method would be of identifying the emergency and how you can understand what's going on. So it's almost sort of vessel awareness of the system and looking at how you can understand the health of each individual component. It's a very difficult one when you're dealing with a system that is from remote, and you could spend months before you actually have access to address any issue or any risk involved. So part of the design is trying to understand where the potential risks are, and how you could identify those risks if something went wrong. So it's a key element of designing a robust autonomous system.
Right. Thanks, Hugh. That was good. And there is a question specifically for you, actually, about a different kind of risk, and that's development risk. How did you handle that in your project, and did you have a formal process?
Yeah, that's a nice difficult question, that one. Development risk is when you're working in an area where there's quite large amounts of development and new technologies being applied, is constantly sort of on the forefront of how you're assessing what development you're working on. We didn't have a formal risk. The risk has to be understood by the engineers and by the management involved in those systems. So there's always a constant communication about understanding where you're introducing risk and where you can be removing risk. for a system that is operating, say, in a harsh environment. Risk avoidance is very key. So most development is aimed at trying to reduce risk, and that's quite a key area. But there's times where you have to balance developing, introducing development risk while trying to remove risk from other areas and other systems.
Okay, Hugh, that was great. Well, thank you everyone for your questions. I think we've tackled them all, which is great. We have run over time, which I apologise for. But I'd just like to hand over to Geraint really to close the webinar for us. Geraint.
Yeah, thanks very much, Tim. Well, wow. If that was a taster of what we would have got at a full weekend at Cowshot, then that was really encouraging. I'm especially grateful to Matthew and Rahul for talking a little bit about their projects. And I'm even more convinced that we were on the right lines in launching this competition. So there was a question that came up and said, are we going to do it again? Yes, we will try and get on the water next year in 2021. We actually had the council meeting yesterday when we discussed that we need to relaunch pretty soon. We discovered last year, I think, that we want to get this into the view of students early in the academic calendar. And so the aim was to get a launch out really by September, if at all possible. And so please, what I would ask you all to do is to pass the word around. We are still aiming to do this. We think it's really worthwhile. And as I say, today's taster was just really affirmation that we were doing the right thing. Last of all, what I should do is I'm just gonna do this. Can you all see that? That's just to acknowledge our sponsors. I think it's really important to understand just how much backing from the industry members of the council this competition has got. They've all put real money behind this. The catamarans have to a large extent been built, and John Downs from the University of Southampton is on the webinar today and has been largely leading that. And I'm very grateful for him for the effort he's put into that. And yes, we want to get these things on the water next year. So thanks very much for the patience by the industry members in keeping their money in this, and we're really looking forward to doing it next year. So thank you all for your time today.
Thank you, Geraint. And thank you everyone for joining us. We'll put a recording of the webinar today, edited where necessary, so we can share with others. And please do point your colleagues at it if you think it would be of value to them. Thank you very much, everyone, and thank you for your time. Goodbye.